Take a look at the structure and some properties of our amines. So for example, our amine, similar to our carbon, generally can have 4 different things attached to it, right? The lone pair does count as a thing. And so if those R groups are different, we have 4 different things attached. So is this molecule chiral? And the answer is not really. And that's because the lone pair can invert easily. This isn't true for phosphorus. Phosphorus can be chiral. So instead of the lone pair being on the top, it can just move down here on the bottom. It can invert, and then you just flip everything here. And then if you think about R and S and just arbitrarily, assign priority to R1 through R3, you can see that one will be the R version, and the other one will be S. So technically can be chiral, but not really because it's just going to interconvert. It's sp3 hybridized. Right, we've got 4 different things attached, or it could be sp2 hybridized, right, depending on the resonance structures that it has. And we'll see examples of that later on. You can hydrogen bond. Remember, hydrogen bonding is between hydrogen and then either fluorine, oxygen, or nitrogen, 3 of our very electronegative atoms. And so this can indeed do hydrogen bonding. That's kind of what keeps your DNA together, as we'll see. But it's not as good or not as strong as an OH hydrogen bond, right? Oxygen is more electronegative, so it's just not as good. So for example, if you look at the boiling point of propane, ethylamine, and ethanol, it goes about where you expect, right? Propane gas, that's what you use in grill, has a very low boiling point. Ethylamine, much higher than the propane, but not as high as ethanol, which is all the way up at 78 degrees Celsius. And then, of course, since we can have primary, secondary, tertiary amines, they can have different boiling points as well. So, for example, here's our tertiary, or secondary, and then our primary, you'll notice they all have the same carbons, so they all have the same mass. This one's down here at 3 degrees Celsius. This one's up at 34 degrees Celsius. And then this one's 50 degrees Celsius, right? So the more NH bonds that you have, the more hydrogen bonding you have, and thus the higher boiling point, right? So in both of these examples, when we go left to right, we either have more or stronger hydrogen bonding. Nothing out of the ordinary there. The final physical property of amines is that they generally tend to smell. And they don't smell good either. They smell like fish. So rotting fish has like a lot of amines in it. And so if you think about what you do with like kind of fishy food is you put some lemon juice on it. And so that has to do with the amines, right? So the amines are the source of the smell. So I'll just put R3N. And then when you add lemon juice on it, lemon juice is acidic. So it's going to have H pluses, and that comes from the citric acid. Right, lemons have citric acid on them, which contains carboxylic acid groups. And so that's that H plus. And so the amine from the fishy smell, normally it'll go ahead, evaporate, and then it'll go into your nose, into the little sensors in your nose, and then it'll tell your brain that, hey, this smells fishy. But when we pick up this H plus, we form an ionic compound. And when it's ionic, its boiling point is going to be much higher, and so it's not really going to evaporate. It can't get up into your nose thus, and then they can't send a signal to the brain, and so you essentially have no smell, right? So that component that causes the smell is still there, it's just no longer reaching your nose.